So you should be seen but not heard sort of arrangement. And what I hope you'll take away is get a sense of how much fun we can have at a math circle and plant the idea of trying to begin something like this in your community if you have not already done so. And if you have, hopefully take away some ideas for other topics that you might try with some of your students. What we're going to do today is a little, I won't give away too much, but it'll be a curious little probability investigation that is suitable for either a high school group is ideal, that's kind of what the topic is pitched for, or an advanced middle school group, I imagine, could also do a lot with this idea. And this particular circle, this topic is originally due to Paul Zeitz, a professor who is out in San Francisco and a good friend of mine. And I've seen him present it a few times, and I've always wanted to try this with some of you myself. So today is a big day. I've handed out some name tags, and I'd love to make sure that everybody has one if you didn't get one already. So if you're here as a student and you haven't got a name tag yet, just let us know. Yes, we're all set. Now let's see if I can actually read them. I'm going to say hello to some of you. So we've got Van. So my last name is Vandervelde, so that's excellent. In fact, my grandfather was called Van because no one wanted to, because I think he didn't like his first name. His first name was Cuthbert, and so he went by Van. And Bertie, and Noah, and let's see, is this Tommy? Hi, Tommy. Glad you could come in, Michael. And how do you pronounce this?
Sangun.
Sangun?
Sangun.
Sangun.
Yeah.
Sangun, great. Sangun's sitting front and center. That means I'm probably calling you first. I need to practice your name, Sangun. Good, and Jared. And then Johannes. Nice. And then we have, I met Jesse. And Smita. Christine. And Megan. Sorry? Aisha. And then, oh, we saw Tom. Okay. So I'm going to get us started today with with a little activity. I want you to all think of a random number, a random integer from 1 to 10. So you got 10 choices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to hand out, don't tell anyone your number. Don't show anyone your number. Just write it down. They're going to take, in fact, you should take 2 index cards. You're going to need these, you're going to need a second card in just a few minutes. So take 2 index cards. Think of a random number from 1 to 10, and then very secretly write it on an index card, and we'll let someone here collect it. How about Jared, since you're already... Jared's going to take all the cards, so get your card to Jared once you've got your random number. And then we also need to know how many of us there are here, so we're going to put someone else to work. Maybe, Ben, you're in kind of a nice position. Can you count how many participants we have? We'll need to know that. 15. So, as Jared's collecting, let me ask you, if we've chosen numbers at random, then what's the probability, say, that you wrote down the digit 7? It should be 1, so Michael says a 10. And then Michael, if we have 15 cards here, then how many of them would you expect to be 7s, roughly? 1 or 2. I mean, on average, or won't work out. Let's make sure we've got all 15 here. That's, in fact, I'll just sort them as we go. We've got 9, 5, 1, 6, 7, 3, 1, 3, 5, 8, 7, 6, 7, 8. So how do we do as human random number generators? Does that seem like a reasonable sort of outcome from our little experiment? We got pair of 1s, pair of 3s, pair of 5s, pair of 9s, pair of 8s, pair of 6s, and 3 7s. How do you feel about that? What do you notice?
There are a lot of duplicates.
Yeah, that's interesting. There are no singles. That's curious. What else do you notice? Do you feel like that if we used a calculator, say, and hit a random button 15 times, we got 15 numbers, that we'd probably get something like this? Or is there something about these numbers that is rather unlikely? Or, let me put it this way. I think this is rather unlikely, that if you hit a calculator button 15 times, you get those sorts of numbers. Why do you think I say that? Oh, let me ask Jesse and then John.
Well, because people favor 7.
So that's curious. Did I get lucky, or did I somehow know you would choose more 7s than anything else? I don't know. What were you thinking? That's an interesting observation. Let's look at the odds here. Out of the 15, there were 4 evens and 11 odds. How likely is that to happen? Well, I don't know exactly. Does anyone know off the top of their head? Actually, do you know what's the likelihood of getting a 4-11 split on something that ought to be roughly 50-50? Have you learned how to compute something like that yet? What does it involve? Do you know, maybe? Yeah, I need some probability theory. And yeah, you need one of those binomial, like those n choose k things. Yeah. Those, in fact, which choose which?
15 choose 11.
Yeah, you need something like 15 choose 11. We won't run through it. It turns out to be pretty unlikely that. So it's true. Humans tend to favor odd numbers. So I'm not going to go any farther with that. We're just getting our feet wet. I'm going to ask you a couple of preposterous probability computations now. Again, just kind of warm up, get you in the right frame of mind for some stuff. So I want to know, suppose you pick any positive integer now, at random. Okay? Any positive integer. And I want to know, what's the probability that the last digit of your number would be 7? I'm just going to toss that out there. What do you feel like? What do you feel like the answer ought to be? You just, yeah. What do you like?
1/10.
I want to be a 10th, right? But maybe you're a little nervous about this question. What's not quite above board about what I just said? Yeah.
You haven't quite defined like the process involved in getting a random positive integer.
Yeah, how exactly do you choose a random positive integer? That doesn't really make sense because there are a lot of them, right? And if there were only 10 numbers, like we just had 10 numbers, then it would be easy. So if I said, in fact, you already answered that, it was a 10. So here's my first thought question. Is there any way to make sense of picking a number, like a positive integer at random, and trying to figure out what the probability is that the last digit would be 7? Like, is there any way to kind of tackle that? In fact, how did you come up with a 10?
I was thinking that for any like large, so if you're just choosing a uniform probability for like a very large number that was multiple of 10, then it would be
Okay.
110.
So,
It's like as it approached it.
does that make sense what Van's doing? He's saying, well, you can't really choose a number at random, but we could say take the first million numbers and pick one of those. And million's kind of like infinity, right? Pretty close. So you take a million numbers, and you choose one of those. And we can answer that question, it's a 10th. What about if we take 1,000,001 integers? From 1 to 1,000,001, pick one of those at random. We check, what's the probability that the last digit is 7?
A little bit less than 10.
Yeah, it's good. Pretty darn close though, right? Just a little bit less than 10. And then you keep going, and then once you hit 1,000,007, what's the probability now that you hit a number that the last digit is 7?
More than 10.
Just a tiny little bit more than a tenth, right? But the further out you go, the less you deviate from a tenth, right? So in some sense, you could say, well, as you go further and further out, the probability kind of it homes in on a tenth. So you could use that idea. Like, that's a very good idea. That's basically how mathematicians handle infinity. They say, well, infinity is not a number. This is a good lesson. I don't remember anything else. Infinity is not a number. It's an idea. And to handle infinity, you almost always use some kind of, well, you use sort of a big number, and then a bigger number, and then a bigger number, and you see what happens as you get bigger and bigger. That's how you really, it's a limiting process. Okay, so you've got this tool now. So I want to know, you pick a number at random, right? Positive integers. What's the probability the first digit is a 7? So let's pick a couple. One idea is I'm going to go with a 9, or a 10. Any other vote?
I'd go with about a 9.
And a second for a 9. Do we have a second for a 10? By the way, why did you pick a 9 versus a 10?
Well, because there's 9 possibilities, because they start with 0.
Oh, so there's the 0 issue. Well, let's see if now I practiced your name, but I'm not going to get it. Singhun. Yeah. So, Singhun, how do you feel about a 10th now?
Well, I didn't really consider, the 0 in the beginning, because if you look at it, you have, so you have 0, 1, you can, in the tens digit, you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Right. So when you're looking at the last digit.
Yeah.
And then a first digit, do you buy that the 0 is no longer a...
Yeah, I see.
You could change your vote?
Yeah.
So we're going with the 9th. Now I have a question now.
I don't know. If you just look at this the same way we saw the last problem, don't like the fluctuations in probability get bigger and bigger as you
So,
get higher.
yeah, okay, let's take a look at this. Let's not commit the cardinal over which is to write directly on that. So hang on, let's see what Van is saying. So if you start with 1, 2, 3, 4, we keep going for a long while. You want to go up to,
Let's go for 1,000,000.
go for 1,000,000. So if you've got all these numbers, what sort of, how many 7s are there as first digits here? Like how close are we to a 9th, I guess is the question. Well,
I think
We're a little below a 9. Or a little above it.
how close are we?
Extremely close.
Extremely close. In fact, you want to change this number just so we have a...
Okay, 9,000, 900,000, 99,000, 999.
So what if we just look from 1 up to here, and you're claiming that up to here, the probability of a first digit being 7 is
1/9.
right on the nose.
Yes.
1/9. Now, can you convince Megan of that?
Megan doesn't look convinced.
Well, as you go up, for example, for 100, there's going to be 100 sevens, but there's also going to be 100 ones and 100 twos. And as you go up in digits to thousands and 10,000s, that same thing will happen throughout.
Let's see. So you're saying that from 100 to 999,
Yeah.
there are 100 to start with 1,
Yeah.
100 to start with 2, all the way up to 100 to start with 9.
Mhm.
So we get a 7th or a 9th of them.
Yeah.
And then the same thing for the thousands, and the 10,000s and the 100,000. So, well, let's see, Megan, is that, does that sound good? But so what was Van was worried about something.
Because it'll change as you go. If you go to like, I don't know, 5 million, then it probably changes.
In fact, let's be extreme. Mathematician is a good skill to have. To go to some sort of extreme. What's the extreme?
6,999,000.
Well, now you want to go up to here. We're going to need another color for that. And now we want to know, well, shouldn't the probability be at least pretty close to a 9th, though? That's kind of what happened last time. What sort of fraction of those numbers start with a 7, Michael?
Well, a much smaller one. I was thinking, I mean, when I thought about it, I didn't go up to 6 million. I just thought about it to 1.9, like 1,900,000.
Oh.
Like I thought of it until,
I see.
because then if you think about it like that, you have like a million numbers basically, essentially starting with 1 from a million to there. So you
Right.
have more than half of them starting with 1s. And it's on the same order of magnitude as the first million numbers we did. So it's like the 1 is completely, is like more
So
like...
the 1 just dominates in the list that you're thinking of, up to 1,999,000.
You can double the number of numbers you use, and then the 1 starts all of them. So like you would feel like there's like this sort of propensity for like 1 to be more common.
So you're saying look up to there, and then it's clearly, like we don't know the exact number, but it's going to dip way off of a 9th.
Oh yeah, yeah.
And then eventually we'll get back to a 9th again,
But you have to go all the way up.
once we get to like 9,999,000. But then what's going to happen after that?
It's going to go back up.
It's going to dip way down again once we get to, I guess 19,999,000 and so on. So we keep getting way off of the 1/9, and so it's a little less. It doesn't.
And every time we reach another power of 10, it'll do that.
Yes, and that's so. Yeah. So what are we going to say? What does that mean?
Well, also it goes up at any point if you pick a random integer,
Yeah.
a positive integer, you're going to get something. The chance of it being a 1, if you were just to pick from 1 to 9, it'll get closer and closer to 1/9. But to pick a 1, to pick like a number starting with a 1, it'll like be much more likely that it'll start with a 1 at any one place you pick.
So I'll just mention there's a fantastic sort of law or rule of thumb about this. Have you heard of this?
Yeah, I heard a program about it. I don't remember what it's called. There's like something
What's the general idea?
that a lot more, if you picked all the numbers like batting averages, like sizes of rivers, that you would end up with a lot more numbers that started with 1. There's like it says something like 1 over ln.
Yeah, it has to do with, there's a logarithm that appears for strange reasons. That if you just take some data, any kind of list, like income tax returns, take all the digits that appear there, you ought to get more 1s than anything else. And that the percentage of 1s is predictable, but it's not a tenth. It has to do with the natural log of a number. Because I don't have it at the top of my head, I'm not going to try to guess. But so digits are there's a lot of fun. You can have playing around with these ideas, and you have some good background or a good foundation from which to take off on what we're really going to do. This is all actually going to warm up, just to get you thinking, just to make sure that it's not too early on Saturday morning. So here's my last warm-up question. It's a quickie. Pick a positive integer at random. I want to know, what's the probability that it contains the digit 7? Give you minute. And then in a minute, we'll go at columns. You ready?
Say that.
Going more than a ninth. That seems safe to say. Because that's, yeah, those sevens can start cropping up in the middle. Okay, so bigger. Let's see, Sam, you want to go any higher than a ninth? How much higher than a ninth? Okay, so I hear an eighth. You are willing to go higher than an eighth? Or are you going to hold? Because of course, this is the Price is Right rules. The person who gets closest without going over is the winner.
I'm not sure what our prize is, but we're probably going very small.
For this piece of candy, are you willing to go more than an eighth? You're willing to go over an eighth. Probability that it contains the digit 7. You can say hold. You can say no. So you're going to say, I'm holding an 8. All right, let's see. How about your name tag is covered by your arm?
Sorry.
Birdie, that's right. Well, how do you feel about an 8th birdie?
Seems like kind of a random value.
Well, yeah, we may not have a chance to really work on it. We're just guessing. Go to all right, back to bid. Okay, he's willing to go to a 5th. 0.2. 5th of all numbers have a 7th somewhere in here. So we'll come here to, this is, that's right, 19 over 100, so not quite 0.2. So you're going to go with 0.19. How about here?
I want to go a lot higher.
A lot higher.
Because I feel like as there become like a lot of digits, the probability that 7 is going to be pretty big. And there's going to be a lot of those.
But once you get to the big numbers, you're almost certainly going to have a 7 in there somewhere, you feel like. So what do you want to say?
I mean, like I want to say 99%.
Ooh, that would be higher. 99%. Well, if their hand's still up, are you going to go over 99%?
Or
I'm gonna say 1.
You can say 1.
Yeah, I want to say as you get
I'm gonna
closer
say
to infinity.
complete absolute certainty. As you approach infinity, the probability approaches 1.
That seems pretty extreme. I mean, Christine, it's kind of a long way from.
But
What's that? Yeah.
I was just thinking, so for each digit, say, there's a probability of 1/10, and 1/9 is the first digit, but we'll ignore that, that it's a 7.
Mm-hmm.
And so as the number of digits increases, basically the more 1/10 chances you'll have that it's 7. So basically you're saying like it, and if you had like if you had a million digit number, then you'd have a million chances at having a 7 in one of the slots.
Well, oh, I see, a million digit number. And so in fact, the probability that you don't get a 7 in each digit is 9/10. And so the probability that there are no 7s in that sort of, in a million digit number is 9/10 to the millionth. Which gets really darn small. So it turns out, we won't pursue that any further. I'll let you play with that a little bit on your own time. But I will let you know that, in fact, the probability is 1. That you're right, that you're almost guaranteed to get a 7 once you go out far enough. So now you have a little idea of what we're playing with. What did I just give you here? This is, well, it says it at the top. This is Pascal's triangle. I left the numbers out because there are a lot of rows here. And now I'm going to present the most preposterous probability computation of all. I want to know, in take a number at random from Pascal's triangle, which we should real quick review, right? How do we come up with the numbers in Pascal's triangle? I imagine that you've mostly seen them, but let's Pascal, it's like, how did that go?
Well, you can do it by starting with one at the top.
Oh, yes. Oh, I should have mentioned this, so please don't fill them out yet. We're going to do take my word for it. Don't fill it out yet. Besides, the spaces get really small, the numbers get huge. We'll come up with a better way of filling
You can
this
look
out.
at it as like 1, 1, 1, and then adding down the columns, or you can think of it as like the probability.
So wait, let's do the adding part. That went by me a little fast. I'm not sure what to do next.
So down the sides, ones.
So put some ones.
In the middle, yeah, there we go. In the middle, you add 1 plus 1, so you get 2.
So that adds to 2.
And then do the same thing, sort of.
So 1 plus 2. So you're saying that I should put a 3 here because it's 1 plus 2.
Yeah, definitely.
And then that's a 3, and then this is a 1 plus 3, 3 plus 3. Right, and you can just keep doing this forever, or until your pencil runs out of way. Okay, so we have this. You can generate all of Pascal's triangle just by adding numbers. That's very good. So I'm going to pick a number at random out of Pascal's triangle. I want to know what's the probability that it's odd. What is the probability that it's odd? And now you get to use that other index card that I gave you. So I tend to do this when I introduce some topic. I want everyone to stare at this for a minute and make just an educated guess, realizing it's purely a guess at this point. I want you to write down on your index card what you feel like the probability is going to be close to. Ballpark. What's the probability of getting an odd number? I'm not going to collect it, actually. You can just hang on to it. But I want you to write it down. So commit to something. How many of those numbers are odd? Pascal's triangle. Let's figure it out. What percentage of them? So does anybody want another minute? Or you had enough? We got it. All sorts of things. Now we need an idea, because in order to get somewhere with this, we're going to fill out our table. We need something in front of us, and we're going to make some headway. But I'm going to kind of shift us into a higher gear, perhaps, or a quicker approach, just so that we can get right onto some interesting stuff. I want to know. I want an alternative to actually writing out all these numbers, because, like we said, they get really big really fast. So let's go to Jerry.
Well, we could just write which ones are odd and which ones are even.
It's only the odds and the evens we care about, right? So you say, actually I have to write 1, 3, 3, 1. I can just write, what shall I write?
O or E for odd or even.
You can just write O or E. You could write, you could put 1 and 0. You could put a check and an X. Just some sort of a scheme or a little notation. You could use whatever you prefer. I'm going to write 1 and 0 just because it's faster for me to write it like this. So we could do this sort of thing. And then, besides, if you use numbers, then you can still kind of add them. 1 and 0 is 1. And that means that an odd plus an even is an odd. That's kind of how that works out. And then what's 1 plus 1? It's 0, because that's like saying that an odd plus an odd is an even, basically. So if I just remember these little rules. So now you can go to 10, right? So, and in fact, here's what I'm going to do. We're going to give you
at least 5 minutes. Write some numbers in, find 2 or 3 people. We have 15, so maybe we had 3, that would be perfect. But not crucial. And take a look at what you've got. I want to get some ideas, some patterns you notice, anything that springs to mind. Look at these together, and we'll reconvene in a few minutes. But this time is yours. You can play around and show one another what you find. And then we'll get some observations up here that might help settle this question.
So that would be really good. If you knew the little rule, and there is a rule, it involves binary and it involves 17 and binary 4 binary. So if you look at those two, you can predict it. It's very nice. It's something that I'll maybe I should take a look at it right after this. It turns out that you can get what we want the other way. But could you? I'm sure you could. Yeah. And it's a good little thing to know. So let's try to. So you can do it that way. You can do it that way. Yeah. Well, at least what? Well, hopefully you get enough observations. That we can explain the one that depends on how we get that capacity to not change anywhere. Well, there's yeah.
No, I don't know.
Yeah, so like all on the edge of the one, so he like closes the forest is the same size.
So what's the virgin law? No, but he's the font. I mean the area. We'll have a lot of what? It's one kind of and then it's oh, where? And then it's a small board. Where is that board? There are some zeros.
is going to happen next after this if you kept going? I think I understand. So,
It can be greater than something in between the two points.
oh, you jumped right. Oh, yeah.
Look, you've got a lot of good stuff. You can keep talking. I just want to start jotting things down that you've seen. Anything at all. Just, so there's some of you have heard of this Sierpinski triangle, but do you know how to spell it?
S-I-E.
S-I-E. The rest of it is pretty straightforward. Sierpinski's triangle. Which is just a little pattern. Now, which numbers make the triangles? Is it the ones or the zeros?
Ones and zeros.
Right, it's like that's true. It's like the ones make the the triangle part, and the zeros count as the space in between somehow. If you want to try to visualize it as Sierpinski triangle. Okay, so that's nice. What else do you notice? What do you notice?
I was gonna say that as like you can look at it as just keep like filling out more rows. It's like filling in more little triangles in Sierpinski's triangle, which causes the unshaded area to approach 0.
All right, so you have a conjecture already about how much space there is compared to how many zeros there are versus how many ones. And the conjecture is that eventually the white space will completely overshadow the dark space. All right, so and let's see if we can confirm that, or just assume it.
So we have the space for the conjecture is that the space, which is the zeros, completely outnumbers, or I'm not quite sure the best way to write this. Outnumbers the sides of Sierpinski's triangle, which are the ones. And there's probably a better way to phrase that, but anything else you know we can prove that? Oh, you prove. How do you prove it?
Well, if you have it as Sierpinski's triangle, then each time you basically take away a fourth of it, and then that should approach 0.
Oh, so what you're saying is as you keep making, so let me phrase it this way, as you keep looking at bigger and bigger chunks of our Pascal triangle, then you're arguing that you can show that the number of zeros versus the number of ones gets closer and closer to 100%. That's okay. That would be exactly what we need to show, but we need some numbers. So any numerical observations about what's here? After all, we need to count how many of these guys we have, how many ones there are, how many zeros there are. If we're going to figure out some probabilities. What do you see? And for that matter, which chunks of the triangle do you want to look at?
Well, each row the shaded in are the ones, I guess, are power of 2.
Oh, that happens to be the case. Yeah, although y is kind of a mystery. Did you know that? What? That the number of, so what Jared is saying is that if you look at the number of ones in any given row, then it's always a power of 2. You either have 2 ones or 4 ones or 8 ones, or eventually you actually have a row with 16 ones right there. That's kind of clever. I didn't know that.
Oh, I forgot. Well, what else did you notice about the triangle? Does any, like, I know that I've heard some good observations back here about just. I heard the word. What do you think?
Well, I kind of see like triangles of zeros
In between.
like the triangles of ones.
So you're saying there's this sort of triangular structure. You try to draw it rather than write it. You're saying, well, there's like some stuff. And then I overheard someone say it gets duplicated. I think it was either Christine or Dana. It gets, you see that sort of stuff again. And then there's zeros in between. So I'll write our observation like that. And then what happens? Like if you kept going beyond that, what are you going to predict happens? What do you So you're saying this pattern repeats. Where does it repeat?
Like, oh wow.
No. So you predict what's going to happen next if you kept going.
So you're gonna have this repeat in the same pattern as before. So terrible job.
So you're going to get.
That's embarrassing.
At least it's.
Oh no, wait. So that.
Found that.
And then there's one in the middle too. Oh, it's in there. What happens in the middle, guys? So it's not. It's just zeros. Oh, it's just zeros. Yeah, right. It's just zeros in there. Yeah, we'll put zeros in there. And then what happens next? You get one of those and one of those and zeros. How does that help us keep track of how many ones and zeros we have? I mean, that's a handy little observation. But does it really help? Right?
And if you look, it's basically, if you took that step of adding the two below it, filling the middle of the zeros, then you took the additional step of say like zooming out so it was the same size as the original. You can kind of see that it would be equivalent to in each of those little things where we've marked somethings here. It'd be equivalent to filling in a little down pointing triangle of zeros. Right? If you
Yes, that's right. I understand exactly what you're saying. You're saying if we do the next step and then kind of step back so it looks this size, it would be equivalent to kind of cutting out a little bit of each.
mean that each step we're cutting out a fourth of the part where there could be one, a fourth of the part where there could be ones, and that's right. And then the number of ones at that point is.
So now you're feeling pretty good about the fact that we get more and more zeros compared to the ones, and I'm starting to feel that way too. How are we going to compute, say up to this stage, how are we going to compute the probability that we get, say, an odd number? Remember that was the original question. What information would I need to know to actually compute the probability that up to, how many rows is this, by the way? We'll call it 16 rows. We'll say that each of this stuff, this was like a 4x4 starter block. What would I need to know to actually compute the probability of getting a 1, an odd number? I need to know, let's see.
Well, you need to know what you're following. It's like get the next one. I mean, you can just figure out here, you start out with one that's the first little top triangle.
Yep.
Is 3/4 of them are ones. And then you have 3 more of those, but then you have a whole nother one that's empty.
Oh, okay, so the 3's going and the 4's going. Oh, so you're coming down to saying, well, if you count how many numbers there are, then we'd also need to know, so we need to know how many numbers actually appear so far. I'll say number of entries, perhaps. And then we'd also want to know how many of them are ones, exactly. So the number of ones. That's how you compute the probability. How many, yeah, so how many ones are there? So you said, where did you get that number 136 from? And how are we going to count the line? Yeah.
16, 17.
Oh, so this is a triangular number. Brilliant. So, this is 16 times 17 over 2. So the number of entries is that. Whatever that works out to be. 8 times 17. Yeah, 136. How many ones? Now you can do this the hard way, or you can use a brilliant leap of. So let's be challenging. I want you to count the ones, but I don't want you to actually count every single one. I want you to use a little shortcut. How can you count those ones?
It looks like there are a lot of equal packets of ones.
Okay, yeah, you got some ones here, but then you've got the same number of ones in each of those. It repeats. At least we think it repeats. We haven't actually completely convinced ourselves of that yet.
Either we found out how many was 1.
Yeah, how many ones are there in this little block? You got 9, 9. So the 9 ones here. All right. So how many? We got 81. Oh, you should just.
It was 81.
Does that? So those numbers are. You recognize those numbers, right? 9, 81. Those are all. Well, there are a lot of things. What's significant about those numbers, man?
The ratio remains the same. Like in the smaller triangles to the larger ones, ratio of ones to zeros. I think it's always going to be 1 to 9.
Oh, let's see. So you're saying we got a 0 here and 9 ones. And this is 9 1 and 9 1. And then we get all these extra zeros coming up in the middle, but we have each of these little blocks is identical to all the other ones, so they're all 1 to 9. Yeah? Yeah. Did you have an idea? Okay. Let me ask you this. If you went to the next stage, so here we get a whole other big block. Oh, rats. I did the Cardinals. If you go to the next stage here, how many ones will there be now? I'm going to try to erase that for these. Tissue. A little bit of tissue. So, Van, what do you think?
I think that we're kind of going about this like the slow way. I think there's like a quick little shortcut we can take, and that's if you if you look at our kind of fractal-ish diagram there, you can see that at any given point, like so the number of so say like we call every time we add the two we add the two self-similar structures below and fill the middle with zeros.
Yeah.
That's called a stage.
Yeah.
First you can note that a stage happens every power of 2 steps.
It's what it looks like. Yeah, we've got 16 rows, and then it'll be another 16 rows to get to there, so it's 32.
Because the height of that. So like if you just look at our if like the triangle we made up above, it's double the height of the little triangles. So it makes sense that each stage should happen in double the steps. But then at each stage, basically the amount of space there is left for ones is multiplied by 3/4 because at each point that big thing of zeros basically takes off a 1/4 chunk.
Does that sound good? So you're saying you get 3 times as many ones as before.
No, I'm not. I'm saying that we get 3 times as many spaces for ones as there were last time.
And
But it makes a little more sense if we look at it from like the add and then zoom out perspective, because if you just think, right, then we're cutting away 1/4 out of each of those shaded sections, meaning that so the amount of space left for ones is reduced by 1/4 or multiplied by 3/4.
Yep.
Therefore, like, we could get a formula for the number of ones by saying that it's 3/4 to the power of the number of stages so far, which would be log base 2 of the number of rows.
So you're saying that each stage, if you take another set of these, that now there should be 3/4, that the ratio of ones to the total amount should be 3/4 what it was before, if I'm hearing you correctly.
And then you can find the number of stages so far that by
Sure.
log base 2 of the number of rows.
Does that make sense to everybody, that there ought to be 3/4 as many, that the ratio of ones to the total thing ought to be 3/4 what it was before? Either by sort of zooming out, like you can think of it as sort of cutting out the middle of everything, or you can think of getting, now you have 3 times as many ones, but you have 4 times as many entries, if you want to look at it that way, because you have 4 of these triangles worth of roughly 4 times as many. We're sweeping a few tiny details under the rug. So as you go stage after stage, we're getting 3/4 times 3/4 times 3/4, and of course that eventually gets as close to 0 as you like. So let me ask you 2 things. I think we'll try to wrap everything up here. How do you feel about this so far? Like, how close do you think we are to really nailing this down? Or what are you worried about, if anything?
I think assuming that the pattern goes on like this, I think we got it pretty well.
Right, so there is this question of,
Because like we looked at the picture that we
Yeah.
drew for like a pretty small, relative to the entire thing.
Yeah.
We drew out like a picture that's pretty small, like a small picture of the entire triangle, and yeah, it probably does continue that way, but like we haven't really shown it.
what if it does something different somehow in a few minutes? Is there any way that could happen? Like, what's going to happen next? What's this bottom row look like? What should this row look like?
Are they colored ones the odds?
Those are the odds.
Initial.
It's like all ones. So what's the next row look like if you keep adding them together?
It should be a
So
triangle.
if you get all zeros, wait, but if you get all zeros, then you're done.
You get all zeros.
Except the 2 ones. Except the 2 ones on the end. And then what do those 2 ones do when you start?
And they self like.
Yeah, they kind of create a triangle, and then you get a whole new row of ones. Actually, it hangs together. It's kind of fun to think through how that happens. Now, where should we go from here? Like, so a mathematician, once he solves a problem, always tries to figure out where to go. It's never check, next problem. You know, it's not like doing homework. It's, oh, that was cool. Now, let's see, what could I do with this? And that's the most exciting part of the whole process. That's what actually makes mathematicians get up in the morning each day. Because you get to decide where you're going. So where would you like to go with this? What do you like?
How many numbers in Stupid's triangle are a multiple of 3?
Oh, so what if you take Pascal's triangle and you keep track of the multiples of 3 instead of the multiples of 2, like the odd evens? And you want to hazard a guess? How many of them are multiples of 3? We decided that the multiples of 2 pretty much took over after a while.
What about the multiples of 3?
Well, you certainly wouldn't have any odd multiples of 3. But I think that they'd probably, I don't know if they'd like go away, because I think you have a lot of like, I know I've thought about before, like the multiplying and not doing like the choose, like the row. And I feel like you would have factors of 3 in there, and certainly you have all these factors of 2, so I feel like you definitely have some even factors, even numbers that have factors of 3.
Yeah, in fact, if you sort of keep track of the even odd at the same time as the multiples of 3, you're sort of looking at like mod 6. If you just focus on the
Well, we could find out by, we could do kind of the same thing by just marking each square with a 0, 1, or 2, and doing addition.
You could, yep, and add the 0s, 1s, and 2s. And you should try this, because it's beautiful. You get triangles again, but in a slightly different way. And but you still get this sort of thing. And if you figured this out, you can figure that out. And you're going to discover that how many multiples of 3 are there? What's the probability of getting a multiple of 3? The probability of getting a multiple of 2 was 1.
Is it also 1?
It's also 1. The multiples of 3 take over. Like the zeros eventually just overwhelm the other number. But I'll let you play around with it. There's a little twist. It doesn't work out quite the same way. It's a nice twist. But you won't see it coming until you try it. Anything else? What could you do next? Like if you were running the circle next week, what would you explore? There's like 100 directions you could go, I imagine. What else might you try?
I'm not. I was saying, so according to what we just thought about, right, the probability of finding a prime number in Pascal's triangle is going to approach 0. But for is
oh, so that's a jump. You're saying if you look at any particular prime, the multiples of that prime take over, and so you're feeling you want to say that the probability of getting a prime in Pascal's triangle goes to 0.
But does that mean that for any given row you can say is there a row for which you say there are no primes after this?
Do the primes ever completely die out? That's a very interesting question. That sounds hard.
Well, they won't. If there are still primes, we know that because you add 1.
It's that second row, right, that counts 1, 2, 3, 4, 5. But what if so that's good. There will be primes that occur infinitely often. What if we restrict our attention to the kind of inside that now? Do primes continue to appear? I don't know. To be honest with you, I don't know the answer to that question off the top of my head. See, now you're doing math. You're starting to ask good questions. I had imagined going in all sorts of different, like maybe you could do a pyramid, right, or a 3D Pascal triangle, or maybe you could do, who knows what. So at this point, I'm going to say, I'm going to cut you loose. If you find something interesting in here, like this is good stuff. You should see where it goes. If you find anything interesting, tell me about it. I am here. I am Sam Vandervelde. And most of you are familiar with that word. And I would love to hear about it. So we'll declare officially that our circle is over, and then I've got a special little offer to any of the students here today. But thank you for attending, to everybody, and I.